Hello everyone, welcome to another video of thermodynamics. In this video, we will discuss how a heat exchanger analysis is done based on the first law of thermodynamics. So in this, let's consider a problem first. This problem says that steam enters a counterflow heat exchanger operating at a steady state at 0.075 megapascal, that is 75 kilopascal, with a specific enthalpy of 2431.6 kilojoules per kilogram, and exits at the same pressure as saturated liquid. The mass flow rate is 1.5 kilograms per minute. A separate stream of air with a mass flow rate of 100 kilograms per minute enters at 30 degrees Celsius and exits at 60 degrees Celsius. The ideal gas model with Cp equals 1.005 kilojoules per kilogram Kelvin can be assumed for air, right? For air. Kinetic and potential energies are negligible. Determine the quality of entering steam, that's the X value of the steam, X value, the rate of heat transfer between heat exchanger and its surroundings. So that's Q dot for the heat exchanger, right? So let's see how to proceed. As I always tell you, it's better to start with the schematic. So let's draw this counterflow heat exchangers. You have A1 tube comes here, and leaves the heat exchanger in a separate stream. So basically, this is the casing, and this is the outlet of air, and this could be the inlet of air. Okay, so this is steam entering. Let's say this is 1, and that's 2. Steam exits, and steam air enters 3, and air exits from here 4. Right? So this is airstream, this is steam, and P1 is 0.075 megapascal, and H1 is given in the problem. H1 is 2431.6 kilojoules per kilogram, and then we have exit condition saturated saturated liquid, that's actually X equals 0 condition, and mass flow rate is m dot s is equal to 1.5 kilograms per second. And for air, we have P3. For air, P3 is pressure is not given, 100 kg per minute, and 30 to 60 degree. Okay, so you have P3 is not given, T3 is given, right? And then T4 is given, and also m dot of air is given 100 kilograms per minute. And also a little correction here, that's 1.5 kilograms per minute, not per second. Okay, so steam flows into this direction, and air flows into the other direction. So that's why it's called counter-flow heat exchanger. So let's look at a property diagram. For this case, I'm going to draw a TV diagram. So these are constant pressure process. Each of these, 1 to 2 and 3 to 4, we can consider them as two different processes. So I'm going to draw that 1 to 2 process here at a given temperature. Should be somewhere here, and then flows into that. So how do I know whether this is in here? So let's go to the table. Let's go to table, and I'm going to go to pressure table here. So pressure table is 75 kilopascal. 75 kilopascal here is here, and I'm going to look at what is the Hg value. So Hg at 75 is this. This is Hg 2662, and in between 384 and 2662, the given value is in between those two, so it's in the saturated liquid region. So the given value is 2431.6, so it's between, so it's here. That's step 1, and step 2 is at saturated liquid region. So this is 75 kPa, right? 1 to 2. And then for gas, it's also a constant pressure process. Also a constant pressure process. So it goes from 30 degrees Celsius to 60 degrees Celsius. But you cannot represent that thing with the vapor dome. You need a separate diagram to show that. So if I draw it on a PV diagram, that's going to be constant pressure process. It's like this. 1, 2, 2. This is for air, right? Yes, 1 to 2. Now I'm going to find out what the quality of steam at the entering state. So to do that, I need this equation to find the quality. Quality is related with H1 is equal to HF at 75 kPa plus X1 HFG at 75 kPa, right? HFG is Hg minus HF. So HF, I found that from the table 385.44, 385.44, 84.44. So sorry, 84.44 kilojoules per kilogram plus X. That's actually HF at 25. HFG at 75 is 2278. 2278 kilojoules per kilogram. So then we have H1 equals 384.44 plus, sorry, I need to write for X1. X1 is equal H1 minus HF divided by HFG. I have H1 is 2431.6, 2431.6 minus HF is 384.44 divided by, this is 2278. 2278. And when you simplify that, when you solve that, 24, 31.6 minus 384.44 by 28. 0.69679. 0.679. That's the quality of steam. So the quality of steam at entrance 67.9%. Okay. And then the final question, the amount of heat transfer to the surrounding. So assuming that there's a heat transfer to the surrounding, we can assume the steady state then first law W dot minus Q dot minus W dot plus M dot S, right? H1 plus M dot steam P1 squared or 2 plus GC1 minus M dot S steam 1 and leaving H2 plus V2 squared or 2 plus GC2, and then M dot air entering H3 plus V3 squared over 2 plus GC3 minus M dot A H3 plus V3 squared over 2 plus GC3 equal 0. All right, and then we need to neglect the potential and kinetic energy changes. So that term cancel to this term cancel to that term. So should be before, right? These are all fours. 4, 4, 4. Cancel to that, right? And then potentially changes, cancel to this, and this cancel to this, right? Let's see, this cancel to this, right? Now everything there, and then this is not a work producing device. Heat exchangers for heat exchangers, W dot equals 0. There's no work production. So now Q dot minus M dot S H1 plus minus M dot S H2 plus M dot A H3 minus M dot A H4 equal 0. Now we can consider, we can find this H1 is already given. We can find H2. So, and M dot S is given, M dot A is given. So we have Q dot is equal to m dot s h2 minus h1 plus m dot a constant specific analysis cp cp t4 minus t3, right? M dot so h2 from table, h2 is hf at 75 kPa because it's a saturated liquid, so it's 384.44 kilojoules per kilogram. You already had that value. Then q dot is equal to m dot s, it's 1.5 kilojoules per minute. So for seconds, it should be 1 minute is equal to 60 seconds. We have to divide this by 60. H2 is 384.44 minus 23.236, sorry, 2431, 2431.6. That's H1 of steam plus m dot air is 100 times 1.005 for Cp, and then T3, T4 is 60, and this is 30. So remember, when you put this to should be in Kelvin, but here in this case, if you add 273 and then it's subtracted 273, 60 minus 30 equal to whatever you have, right? And it should be also divided by 60 because this is per minute as well. Right. So you're gonna solve this 1.5 divided by 60. 1.5 divided by 60 times 384.44 minus 9431.6 plus 100 divided by 60. 1.005 times 30. Again, you get negative 0.929 0.929 kilowatts. So this term actually represents heat input. So heat input is negative 929 kilowatts, sorry, watts. So this is 900 negative 929 watts, right? And what is the heat output? So heat output is 929 watts. This is a heat input is negative, means it's actually heat output, right? So first, what we did was we found the X value, which is the first answer, and then we used the first law of thermodynamics. Here, what the main assumption is, heat exchangers does not produce any work. Those are not work producing devices. And the system we considered was this entire thing, right? So we, and then outside the system boundaries surroundings. So during the heat transfer, heat is transferred from steam to air, and but some steam is some heat escaped from the casing, And that's what that steam, that energy is, 929 watts. Well, thank you very much for watching this video, and see you in another one.